Although statistical methods are used from ancient times, but non-parametric methods have been used from 19th century only. Uh, the term non-parametric was first introduced by Wolfowitz in 1942, but we can find scientists like non-parametric test in the Fisher's seminal book in 1925. So we shall start this module with limitations of parametric inference. Then we shall discuss two important concepts, namely distribution free and non-parametric distribution free statistic. Uh, for example, if we consider uh, samples n observations from normal mu1 population, then we find that the distribution of summation xi minus x bar square is chi-square with n minus 1 degrees of freedom. So this distribution does not depend on mu, and hence this particular statistic, that is summation xi minus x bar square, is termed distribution free. But if we consider some other distribution, say Cauchy distribution with location parameter mu, then the distribution will be no longer chi-square n minus 1. Now, next we introduce the concept of a non-parametric distribution free statistic. For example, if we suppose we have observations, say n observations, n independent observations from a continuous population having symmetry at the origin, and if we consider the statistic summation I from 1 to n indicator xi greater than 0, then the distribution of this sum of indicators is binomial with parameters n and probability of success probability x1 greater than 0. Now, due to symmetry, this probability x1 greater than 0 is nothing but half, and this is true for every underlying distribution having symmetry at the origin. Therefore, the distribution of summation I from 1 to n indicator xi greater than 0 is independent of NEF, and this type of statistics are termed non-parametric distribution free. But in our forthcoming modules, we shall refer such statistics as non-parametric, and the procedure will be referred as a non-parametric. Next, we shall give some exploratory data analysis explaining the need of non-parametric inference. We shall discuss some non-parametric methods, and actually we shall start with the shortcomings of a parametric inference. Actually, in parametric inference, what we do, we assume some distributional form and then do the appropriate statistical analysis for that statistical model. But in most of the times, this data, the distribution of the data is not known. So what to do? It may be possible that one adopt some parametric inferential procedure for this type of data, and he will end up with some conclusion which may not be valid for this data. So better we start with some real life example. Suppose the average weekly sales of a new cell phone are collected for 12 consecutive weeks from a particular shop and are given below. So there are 12 sales figures, and the average weekly sales was 125 units for the last year. It is known. So the sales, so it is of interest to know whether the current year sales exceeds the last year sales. So this can be made in terms of a statistical hypothesis. If mu is the true weekly sales, then we are interested in testing the null hypothesis mu equal to 125 against alternative mu greater than 125. So this is a single sample problem, and if we assume that now normality of the data, then the usual statistical test in this context is a single sample t-test. If we run the R code for the t-test, we get the p-value as 0.56 and the value of the t-statistic as minus 0.156 and the corresponding degrees of freedom as 11. So this p-value is quite high and far from 0.05 or 5% level. So the evidence is not enough to reject the null hypothesis. Therefore, the conclusion in this case is that evidence is not sufficient to conclude that there is an increase in the true mean weekly sales. So it might be possible that this is the final conclusion, but this final conclusion is not validated because we are using t-test, and t-test is not a test. T-test is a parametric test based on some assumptions. So in actually these t-tests are valid provided observations are drawn from a normal parent population or the sample size is sufficiently large, say at least 30. In our example, we have only 12 observations, so we must check whether the underlying population is normal or not. What we do? We use some simple data descriptive techniques. For example, we use some histogram. Actually, histogram is the simplest descriptive method to check the shape of the data uh, in a easy manner. In particular, a symmetric bell-shaped histogram is an indicator of normality. So when we plot the histogram, we find that this is not symmetric and this is not bell-shaped. Actually, the histogram looks like some U-shaped curve. So this data is far from the normality. At least the histogram is concerned. Naturally, the sales data as shown by the histogram is far from being symmetric. Therefore, the sales data cannot be suspected from a originated from a normal distribution. Actually, there are some other confirmatory tests. For example, one is the normal QQ plot test, QQ plot, and this is the simplest and perhaps the best way to check this to use for the normal QQ plot. In a normal QQ plot, the quantiles of the observed standardized data set are plotted against the corresponding quantiles of a standard normal distribution. And for normal parent, we expect that these two quantiles match. So for the normal parent population, the result should be a plot of points over a straight line, or at least scattered over a straight line. If you see the QQ plot, we find that the observations are scattered and the red line, actually ideally points should lie on the red line, but there are so many points which are above and below of the red line. So it is confirmed that the underlying distribution is not normal. We find that the observed quantiles are too far from those of a standard normal distribution, and hence the normal assumption is not reasonable. T-test is not trustworthy for the sales dataset. So we have used, we have get some p-value of 0.54 is not significant to reject the null hypothesis. P-value is not valid as the distributional assumption is not validated. What we observe? Actually, in the previous problem, we have adopted a parametric method, that is a student t-test. And a t-test requires the estimation of the assumed population parameters. Here we have, for the t-test, we assume normality, and naturally such methods require a number of assumptions, as for example normality of the underlying data set, but there are situations in which one or more of these assumptions may be violated, so that the traditional or parametric methods of analysis lacks appropriateness. So we find that the data set for the sales example is not normal. Still we have used some t-test, and therefore the results are not validated, so we can't use the observations or the inference obtained from the t-test. In parametric methods, we use some distributional assumptions and estimate the parameters, and then use the appropriate techniques, maybe likelihood ratio test or maybe Neven-Pearson lemma, to get some testing procedures. But if the distributional assumption is not valid, then these traditional methods are not actually adopted, because they may be misleading. So in practice, we have a variety of data which are non-normal. For example, we can have positively skewed data where the concentration is towards the higher values of the data set. We may have, for example, we can have a log normal distribution or gamma distribution which is positively skewed, which gives positively skewed data, and in those cases the normality assumption and the corresponding t-test is not valid. There may be also negatively skewed data. Here also the normality assumption is not valid, so we can't use t-test. The histogram or the data looks like J-shaped. Actually, we use exponential distribution in live testing problems. So this in this case we find that the data is J-shaped, that is it decreases over time, and therefore since this is not symmetric, we can't use normal distribution for the appropriate analysis. And there may be also some U-shaped data, and U-shaped data, though it is symmetric, but is not bell-shaped, and therefore we can't use normal distribution and normal derivatives as Ttest and Ztest for our purpose. And finally, there could be some mixture data where we may have some 2 peaks or 3 peaks, and so normally this here the normal assumption is not valid and we can't use the appropriate Ttest. So what to do in such cases if we have data from log normal distribution, exponential distribution, or gamma distribution? If we don't know the parent distribution, if we know the parent distribution, then we can use the appropriate parametric methods. But in most of the cases, the distribution underlying is not known, and we have to use some inferential procedure, and non-parametric inference is the only alternative in such cases. So since there is no parametric assumption, we need to adopt the opposite of a parametric method, that is non-parametric methods, which are an alternative series of statistical methods requiring very limited assumptions about the data. Actually, non-parametric methods assume that the observations are independent and they are from a continuous population, and a range of methods are available to adopt in different circumstances. So parallel to parametric inference, there are a number of methods in non-parametric inference for the same purpose but with limited assumptions. In particular, non-parametric methods make no specific assumptions about the distribution of the data except continuity. So now we shall discuss the pros and cons of non-parametric methods. The main problem with parametric inference is that if the assumed distribution is not correct, then all the efforts might went into vain, and the best, that is the efficient, can become the worst. For example, in the sales data we have used Ttest without knowing its distribution. So we find some p-value and some t-statistic, but the results are not valid as the distribution of the data is far from normal. So if we adopted the non-parametric methods in such cases, then we can accommodate non-normal data for analysis efficiently. So if the data is non-normal, we can still use non-parametric methods without knowing the distribution of the underlying variable. And the second advantage of non-parametric methods is the robustness, that is being efficient even under the assumption violation. So in parametric inference we assume some particular distributional form and some particular distribution with some certain parameters. If the distributional assumption is violated, then these results are of no use, and in contrast to these methods, our non-parametric method is robust, that is remains efficient even when the assumptions are not validated. But we can't use non-parametric methods blindly, and it is not always the most desirable procedure, because most of the non-parametric methods use only ranks or signs of the observations, discarding the further features of the data. So since we use only ranks or signs of the observations, we just discard the other features of the data. Only the sign of the observations are considered, the magnitude is ignored, so there is a loss of information. And secondly, they are usually not as efficient as their parametric counterparts when the assumptions are made. So if it is known that the underlying distribution is normal and we use a t-test, then t-test is the most efficient, even if there are some non-parametric methods for this problem. So finally, although non-parametric methods require fewer assumptions, but they are used rarely in practice because most of the non-parametric procedures discard information, so there is a loss of information, and loss of information in reduced efficiency. And specifically, when we compute ranks for a highly skewed data, actual values are discarded, leaving only their order. So loss of information limits the ability to detect true effects as compared to the parametric methods. Non-parametric methods are primarily used, or should be primarily used, in situations when assumptions are grossly violated, that is when severe skewness in the data is present. That is, if we find a sign of severe skewness in the data, we must use non-parametric methods. And if the deviation from normality or if the deviation from symmetry for the data is very nominal, we could use the normal t-test, and in that case t-test will be efficient. So we shall discuss in our next series of lectures what are the basic ingredients of non-parametric methods, and what are the basic methods adopted in non-parametric statistics, how estimation is done in non-parametric methods, and how testing is performed in non-parametric methods. So we have discussed the limitations of the traditional procedure, that is the parametric procedure, and introduced non-parametric inference. We have given some real life example to explore the concept of non-parametric inference and of course the need of non-parametric inference. In our next modules, we shall discuss non-parametric estimation in terms of U-statistic and also provide some testing procedures, of course non-parametric testing procedures for single sample and two sample problems. And finally, we conclude with a consideration of the comparison of different non-parametric tests, that is in terms of asymptotic relative efficiency.